In the last class, we have discussed about the Fourier integral, and then towards the beginning, we have considered two simple examples on Fourier series. One is the delta function, which we say we found that the delta function, the Fourier transform of delta function is of the order form e to the power I k kx x0 kx0. So in k space it's an oscillatory function. If x0 happens to be 0, then it becomes a constant. And secondly, we have considered the function which is a constant in position basis, and we found that its Fourier transform is a delta function. Now we consider a function called box function, which is defined as this: f of x is equal to h for mod x less than a and is 0 for greater than a. This is also called a single slit aperture function, because in Fraunhofer diffraction, when a plane wave propagating along a particular plane wave propagating in a particular direction falls on a single slit, the slit function is this, and the wave that comes out from the slit is known as the single slit diffraction pattern. We shall see that this is the same. So we calculate the aperture as Fourier transform of this function, which is 1/2 pi integration f of x e to the power minus I kx dx. Integration actually ranges from minus infinity to plus infinity, but for minus infinity to minus a, the function is 0, so we integrate it basically between plus minus a. And let me write it first in the general form. Then it is h upon root 2 pi minus a to plus a e to the power minus I kx dx. When we integrate it, we get h upon minus I k root 2 pi, and in the upper limit it is e to the power minus I k a, and lower limit it is e to the power plus I k a. So there is this much is minus h times minus 2I sine k a, and in the denominator minus I k root 2 pi. Minus minus goes, I goes, so the result is h a by root 2 pi. This a comes from this we write it sine ka by k sine ka by k, which we have written as ka, and it's a damped sinusoidal function. So see that it is a damped sinusoid. So what will be its form? Its form will be like this. This is a of k, this is k axis. Note that at k is equal to 0, it is ha upon root 2 pi, and this function will be 0 at ka. At ka is equal to plus minus n pi. So for k is equal to plus minus n pi by a. The function will be 0 at these points. So this point is pi by a, this is minus pi by a, this is 2 pi by a, this is 3 pi by a, again this is minus 2 pi by a, 2 pi by a, and this point is minus 3 pi by a. This is a damped sinusoidal. Because of the presence of this factor, the wave dies down and it is appreciable only in this range. So it is appreciable over delta k is equal to 2 pi by a. This is 2 pi by a is the range over which a of k remains finite, and on the other hand this function remains non-zero or appreciable over 2a. So if we multiply this delta k, delta x is equal to 4 pi. This function, this envelope function, is the envelope function that we see in the double slit or any other higher number of slits wave function. This wave function is known as the envelope function, or it is known as sin C function. It is a very important function in diffraction optics. Now we consider as the second example, we consider the double slit aperture function. As the fourth example, we consider double slit aperture function. The double slit, as you know from your knowledge from physical optics, it is two narrow slits separated by a distance a which is greater than the slit width. If we plot the function or slit function, this looks like f of x, it is 0, then it is symmetric. We say that it is centered at a and this one is centered at minus a, and the width is 2v of each. So the points, this point is, this is plus a, this is a plus b, the right end of this is a minus b, this one is minus a plus b, and this end is minus a minus b, and the height is h. This is the double slit pattern. So we define double slit aperture function as if it is less than a minus b and greater than minus a plus b, this is zero line, this has been written less than a minus b and greater than minus a plus b, and it is again h in this region, and 0 else otherwise, and 0 otherwise. So the Fourier transform of this is root 2 pi, we multiply with this, it is f of x e to the power minus I kx dx from minus infinity to plus infinity. So this will have only two contribution, ones from here, h plus tx. So upon integration from first I get h by minus ik, and then we get and from this we get h by minus ik, this is the function. You see, this is ik and this is also ik, so we take ik out, h times e to the power ika out minus ik in the denominator, and we are left with e to the power minus ikb minus e to the power plus ikb. This part is equal to minus 2I sin kb. And here we will have also h upon minus ik. E to the power minus ika is taken common, so we are left with e to the power minus ikb minus e to the power plus ikb, which is again this. So this minus sign goes from this is also minus twice I sin kb. So minus sign and I we are getting rid of, and so we are left with twice h by k sin kb times e to the power ika plus e to the power minus ika, which is equal to 2 cos ka. So the result is 4h by k sin kb cos ka. If we write it with rearranging, this is 4ha cos ka sin kb by kb. This is known as the diffraction term, which is same as the single slit pattern. This is the diffraction envelope. And this is the interference term. That is to say, if we have only single slit, the diffraction aperture, diffraction profile is given by this, and due to the presence of two slits, there will be interference of the light diffracted from the both slits, and this cos ka term is the cos ka term represents interference between the diffracted rays from the both the slits, and it is called the interference term. If we plot a graph of AK, then we see that this envelope function is like this. We will have negative parts too. So this is the envelope function. Envelope function, this is sine kb by kb, and this part is minus sine kb by kb. This is the diffraction envelope, and within this diffraction envelope we will have the interference terms. Like this. The red one are the interference term. And if we take the complex conjugate it or square of it, we get the double slit intensity pattern, which looks like this. This is the central maxima in these are the bright lines that you see on the spectroscope. So this is the double slit diffraction pattern. Here we have established that the diffraction pattern, so for the Fraunhofer diffraction pattern is concerned, it is just the Fourier transform of the aperture function. For grading, such thing can be continued to grading where there is a periodic arrangement of slits along the x-axis, and we calculate the envelope, the Fourier transform of it, which gives you the grading pattern. Now, as the next example, we shall come to triangular wave. We shall consider triangular wave as the fifth example. In the case that we are going, in the example that we are going to consider onwards, sometimes the mathematical manipulation may become complicated because it may involve more few terms, and which will take a longer time to work out over here. So in such cases, what we shall do, we will outline the basic steps and finally code the final result. There are examples where special tricks are needed for the evaluation of integral that I will work out in detail. So first I will consider the triangular wave. A triangular wave, if we draw its, this is x-axis, this is symmetric, minus a, 0, plus a, and say this height is h. So the function is f of x is equal to h times a plus x when x is less than 0, greater than minus a. This is equal to h a minus x when x is less than a, greater than 0, and is 0 otherwise when mod x is greater than a. This is the definition of triangular wave, and the wave looks like this. If we come to the calculation of a of k. As usual, a of k is defined as this. Actually the definition was from minus infinity to plus infinity, but for the present purpose it has to be written as so there are many terms involved, and if you go on calculating correctly, ultimately one lands up with h square upon root 2 pi. As I have said, I am skipping the actual calculation, the manipulation. This is the function. And we see that this is a real quantity and as a term sinusoidal again. The peak value is a max is a it occurs at k is equal to 0 and ak is 0 at which this Ka by 2 is equal to n pi or k is equal to plus minus 2n pi 2n pi by a. These are the, and n is equal to 1, 2, 3, not 0, because at n is equal to 0 it has a maxima. So the graph is, and furthermore note that since it comes as the square, so the graph is always positive. It never goes to 0. This is first 0 is at 2 pi by a. This is the graph, and this is 4 pi by a minus 4 pi by a, like this. As the sixth example, we consider asymmetric sawtooth. Let me explain what is meant by asymmetric sawtooth wave, then we shall consider symmetric sawtooth wave. Asymmetric sawtooth wave is defined as f of x is equal to h of x, hx for x less than a greater than 0 and 0 otherwise. So its function, the function looks like this. That's why we call it asymmetrical. And we can calculate a of k. Actually it becomes h upon root 2 pi 0 to a x e to the power minus I kx dx. On simplification, this gives you you do the calculation of yourself at home and confirm with the result that is obtained. If there is any anomaly in any result, do not hesitate to let me know about the shortcomings or the errors or mistakes, and which I shall consider for correction. First thing, you see that it is complex, neither real nor imaginary, it is complex. So if we consider the real part of a of k, this is h upon root 2 pi whole square. You see that at k is equal to 0, at k is equal to 0, real part of a of k is h a square by 2 root 2 pi, because this contributes 1 and this is half, so this is half. And the graph of it looks like this. It is a complicated damped sinusoidal too, because it is a combination of two waves. This has the periods as a double of one is double of the other. It is look like this complicated one. This is the real a of k and this is k. This value we have just quoted here. This is this value, the peak value. Now come to the imaginary part. The imaginary part of a k is apart from this h upon root 2 pi, it is a cos ka by k minus sin ka by k square. We call it h by root 2 pi, then this is k square and this is a k cos ka minus sin ka. To determine the nature of this function at k is equal to 0, it seems difficult because this is sin ka by a. So what we define numerator function is ak cos ka minus sin ka, and calculate the prime of it. N prime of k is the derivative of this with respect to k. So first term is a cos ka, the second term is minus a square k, because here we will get 1a, minus a square k sin ka, and if we multiply it, cos ka. And correspondingly we define the denominator function as k square. So d prime of k is 2k. At k is equal to 0, it is 0, and this is also 0. Again it is in 0 by 0 form. So let us apply L'Hospital rule once more. So this is minus a square sin ka. If we come to this term, this is a square sin ka, this term, this is the, and if we differentiate this term, then we get a cube k cos ka, and from this term we get plus a square sin ka, and 2. So if we apply this with k is equal to 0, first thing is see that a square sin ka goes, so this is minus a square sin ka plus ak cos ka. So the imaginary part of a of k at k is equal to 0 is equal to h upon root 2 pi n double prime at k is equal to 0 by d double prime at k is equal to 0. We have used L'Hospital rule or L'Hopital rule twice. It is 0, so the result is 0. Thus we see that it will be and it is easy to see that it is an odd function, because this is even, this is odd, the denominator is odd, it is an odd, it is odd, and this is even. So this is the combination of two odd addition of two odd function, and which is again an odd function. This is the type nature. I haven't calculated the AK, which is left as an exercise for you. In this discussion we have emphasized on the value, what is the value of imaginary part of AK at the origin. This value cannot be determined as as it stands in its original form, but it is in the 0 by 0 form. If we write this, if we put k is equal to 0, it is 0, and the numerator is again 0, so 0 by 0 form. So we have used the numerator function and the denominator function and differentiated it. If we put k is equal to 0, k is equal to 0 on the first derivative, this is 0 and these two cancels, again n prime is 0 and this is 0. Still it is not determined in the indeterminate form, so we go for the second derivative, n double prime, which is this, and d double prime is this. In this case the denominator function is no more 0, and we find that the numerator double derivative of the numerator is 0, so the function passes through 0 at the k is equal to 0, and it is easy to see that the function is odd one. That is its graph. Now we come to the seventh example, is the symmetric sawtooth wave. Asymmetric sawtooth wave, we find that the Fourier transform is a complex number, so we go to the symmetric wave, is this, and the graph becomes this. And if we calculate, we see that the function is a real odd function, so its Fourier transform will be imaginary odd. And we find that in this case, the a of k, the Fourier transform of symmetric sawtooth wave, is the imaginary part multiplied by 2. So on calculation, sorry, imaginary part I have erased, this will come out to be 2h upon root 2 pi I times a and which we have discussed in detail. So the graph will be of this time, only there is a scaling factor. This is the symmetric sawtooth wave. So we see that the Fourier transform of symmetric and asymmetric function differs a lot among themselves. As the 8th example and the last example of the class of this class, we consider the step function. This is actually the Heaviside step function. Forget about the name, let us define the function and see what happens. In this case, technical some evaluation of the Fourier transform requires some tricks, so I will carry out this calculation in detail to show you the steps. Step function. The function is defined like this. And you see that the function has a discontinuity at x is equal to 0. If we plot the function is like this. And there is a discontinuity. Now come to the calculation of a of k. This is the basic definition. The definition reduces to this form. And you see that this is the oscillatory function. The integrand are oscillatory, so it cannot be integrated as it is in infinity. The integrands are oscillatory. So what do? We use suitably damping factor with it. You introduce suitable damping factor which is the power alpha x with alpha is real, and ultimately we will let alpha tends to 0. This is our calculation technique. So what we do is this. Limit alpha tends to 0. H is common in both the terms, so we write minus h for. In this region, this negative region, the damping factor will be e to the power alpha x, e to the power minus I k x dx minus infinity to 0, and on the other hand it will be limit alpha tends to 0. Here the damping factor is e to the power minus x, e to the power minus I k x dx from 0 to infinity. So this is minus h limit alpha tends to 0. You see, this is actually the integrand is alpha minus I k. So this is alpha minus I k, and we put between the limits minus infinity to 0. And for the second case we write h limit alpha tends to infinity. This is alpha plus I k this is a minus sign, so we put it minus, and in the numerator it is e to the power minus alpha plus I k x. Sorry, x is missing here, x 0 to infinity. We see that due to the presence of alpha factor, this will be at infinity, this will be die off, and the result is minus h times alpha minus I k, obviously with limit tends to 0, and for this it is the contribution will come from the lower limit, so its sign will be positive, h alpha plus I k, and we put both the things within limit alpha tends to 0. So the result is if we take h out, this is minus alpha minus I k plus alpha minus I k. So alpha goes, the result is limit h IH by k. and if we adjust this factor, then some numerical factor will change. And let us see how this behaves. This is the k-axis. It is, note that it is purely imaginary, so it is the imaginary part of it. Now as k is negative, this quantity is positive and goes to infinity. This is the behavior for negative k. For negative k, the quantity is positive and it goes to plus infinity as k is approached from the left. And when k is positive, the quantity is always negative and approaches negative infinity as k is approached 0 from the right. So this is the graph of the Fourier transform. That's all for today. In the next class we shall consider few more examples on Fourier transforms.